And here we go with semester 2. We will start with unit on electrostatics. And this will lead into circuits eventually, and then ultimately into magnetism and electromagnetism. And that hopefully won't be the end of semester 2. We'll see. We should also do optics and then some special relativity and maybe some other modern topics. We'll see where we get. So electrostatics. Now this lesson here is going to run off of a worksheet which is in Canvas, and the worksheet is this one. So this is the first page that I'm showing you. It's on Canvas in the latest module. You should look for the document that says worksheet electrostatics PDF. All right, so for the electrostatics, so first let's start with the structure of the atom. So some of the basic stuff from chemistry. We need to understand what the atom is made of and how it can be altered. So nucleus, and then that which is outside of the nucleus. So let's maybe draw a nucleus for the, well, let's just show the following. Let's say like a plus and another plus, and then maybe some. So we have a proton, we have a proton, we have a neutron. So let's say this is what we have, and then let's just draw some kind of an electron on the outside. All right, so pluses would represent the electrons. No, pluses would represent the protons. So these are protons. And here I have a neutron, so something like that. This would be a neutron. All right, then we have an electron somewhere on the outside. So I'm going to put here an electron. This represents an electron. And this thing is on the outside. So this is the nucleus. All right. So this is the nucleus, and then we have an electron that is on the outside, and then somehow this electron is doing something here. We don't really know what it's doing. It's typical to draw some kind of an orbit. We know that the electron is actually not orbiting the nucleus, but it's typical to draw the something to that effect. So here's an atom, and since I have two protons, I presumably would have two electrons. Maybe I'd put another electron somewhere out here. So let's put another electron, and then we have an actual atom where this thing is neutral, right? So this whole thing would be an atom, and well, I guess I should probably say a few more things about the structure of this thing. One of them is that suppose that you do have a positive nucleus. Right, there's a positive nucleus, and suppose that you do have an electron, and an electron actually moves around. So here's an electron. I'm going to label this with E, and then here's a proton P, and then let's say that this thing does in fact actually orbit. There would be a problem if that was the case. So if a charged particle accelerates, now it's pretty obvious here that it does accelerate, because if it moves along a circular path, and we're going to assume that this is a circular path, but even if it wasn't circular path, similar analysis would apply. So if the electron is moving along a circular path, or if any mass for that matter, and this thing has a mass m, moves along a circular path, there must be centripetal force. There's some kind of a centripetal force that points towards the center and maintains this thing in a circle. Now if there's a centripetal force, then that implies that there's a centripetal acceleration, AC. But there's a problem with that. You don't know that yet, but I guess we will get to that at some point. I think we will. If you take a charged particle and you accelerate it in any way, shape, or form, or whatever, as long as a charged particle, plus or minus, is accelerated, it will emit electromagnetic waves. So what we will have here is, if this electron is in fact moving along a circular path, then it will have to emit electromagnetic waves. I'm going to put EM, and so it emits energy. Now if a particle moving along an orbit here emits energy, then it's losing energy. But if it's losing energy, then well, then it's losing its speed. Now if it's losing its speed, then its orbit changes, and so what we end up with is the orbit would look like this. If in fact the electron were to move along a circular path, or an even non-circular path, as long as it was orbiting, the electron would be losing energy, and therefore would have to spiral towards the proton, and you would have a big collapse. So no electron can move, no electron can orbit a nucleus, because if that were the case, then all of the atoms would collapse, and there would be no atoms, but we know there are atoms, so there's a problem here. So what we generally do in quantum mechanics is we say, well, there's a positive nucleus. So let's say this plus here represents a positive nucleus, and then there's an electron cloud, or rather a probability distribution of the location of an electron. So the electron may be not so likely to be here. Maybe it's a little likelier to be somewhere out here. So I'll try to make this a bit denser, something like that. And then it is less likely to be out here, even less likely to be out there, and so on. The farther away you are from the nucleus, the less likely this thing is. So what I've done here is I put all of these dots where these dots represent a probable location of an electron, and its most likely location, the most likely location of the of an electron would be where I have most of these dots. That would be the highest probability of locating the electron. This is the best we can do. We don't really know what the electron is doing on the inside of the atom. We really have no idea. We know it's there. We know it has, an electron has a mass. We know it has a charge. We'll talk about charge in a little bit. And we know it's there, but we don't know what it's doing. And we certainly don't know what an electron would look like. So, but what we can calculate is we can calculate this region in space where we can determine how likely it is for an electron to be, for example, here, or here, or here, or maybe somewhere out here. And we can calculate the probability, and according to those calculations, we know that the electron is most likely to be in this region here. But what is it doing there? We have no clue. Is it orbiting? Well, it cannot really be orbiting, because then it'd be losing energy. So when it's, at least according to classical description of what a charged particle does. So there's that. And then I'm sure in chemistry you have seen various different types of orbitals. Orbitals would be regions of space that indicate where an electron is likely to be found, or where it is likely to be. For the purposes of this class, you don't have to worry too much about any of that. So actually, let me do this. So this is a wrong image of an atom. It just doesn't work like that, and it doesn't work like that for this reason. This is the best we can do, but of course that doesn't really tell us what the electron is doing on the inside. All we can do here is calculate the probability of finding an electron at some specific location, or specific region, I should say. But still, for the purposes of this class, for the sake of simplicity, let's see, which way should I move? Oh, running out of space. What we're going to do is we're going to say that we have a positive nucleus, and then we have electrons on the outside. So let's just draw like an electron here, maybe another electron here, maybe another electron here, and maybe another electron here. And then, so this is the nucleus. Maybe put a couple pluses here, right, a bunch of pluses, and then we have electrons on the outside. This is what we think of as an atom, because the electron would in fact be towards the outside of the atom. Now, if you look at it that way, it should be pretty obvious that it's difficult to, it should be clear, I think, to see that it would be more difficult to remove the protons from the atom than it is to remove the electrons, right? If I want to remove an electron, all I have to do is grab this guy and just yank it out, and then the electron is gone. But if I want to remove a proton, I have to go all the way towards the inside, alter something within the nucleus, and then yank this thing out. It's a lot more involved. The electrons are sitting on the outside. I have an easier access to them. So it's easier to remove electrons. It should be easier to remove electrons than to remove protons, and in fact that is true. For the sake of all of electrostatics, it's not possible to remove the protons. I mean, that involves a nuclear process, and that is not something that falls within the unit on electrostatics. So you cannot remove, within this unit, you cannot remove protons from an atom, but what you can remove is electrons, and it's easy to remove electrons. Now, how easy is it to remove electrons? Well, let me give you an example here. So let's maybe slide this out of the picture. This is the first worksheet. Now I need some space. This is range. Okay, this is space. So suppose that I have a bunch of atoms. Let's say I have a table. Here's the surface of a table. And within the surface of a table, so let's give it some legs, I have a bunch of atoms. So here's an atom, here's an atom, here's an atom. There we go. And let's put some pluses for this thing. So here's a positive nucleus, positive nucleus, positive nucleus. And then I have electrons on the outside of these atoms. So let's put electrons around here. Now, if it is in fact a table made out of wood, then you really would have polymers here. Polymers are long chains of molecules, so you'd have a little more chemistry here than we need. It doesn't really matter. It comes down to the same analysis. So let's say we have that bunch of atoms lined up like so. Now, how will I remove electrons from these atoms? Well, here's what I can do. There's more than one way to do it, but here's one way. Let's say I take a hand. So, ooh, count well. That's good enough. Here's your hand. And what I'm going to do is I'm going to take this hand and I'm just going to wrap that hand along the surface. And as I do that, what am I doing as I do that? Well, I'm removing a bunch of electrons. So what will happen is let me find an eraser. So this electron here. Oh, that didn't work. It didn't really work the way I wanted to. Doesn't matter. So this electron, oh, I know what happened. Hang on a second. Okay. So as I move the finger across the surface of the table, this still didn't. Okay. Well. This electron left. This electron was taken, this electron was taken, this electron was taken, this electron was taken, this one was taken, and this one was taken. They're all taken, and now they ended up on this finger here. Bunch of negatives on this finger, however many I took. 1, 2, 3, 4, 5, 6, 7, 7, 3, 4. Look at that, I actually did get 7. So I have 7 here. So now what happens is the table has lost electrons. As a result of that, the table as a whole is going to acquire, table as a whole is now going to have a net positive charge because it lost electrons, and then my hand as a whole, because it acquired electrons, is going to have a net negative charge. So you can remove or add or move in general, can move electrons by friction. I'm going to put here by frictional rubbing. Alright, now you cannot do the same thing for the protons. That is, you cannot take your hand and slide it across the surface of the table and remove protons. That just wouldn't, just not gonna happen. But what you can do is you can take your hand and slide it across the surface of the table and then remove the electrons. So you can move electrons by frictional rubbing. Alright, now at this point, you should have enough of information to complete pages. You have enough of information to complete page one of this worksheet. So you should pause the video, complete page 1, and then come back to the video. Now I'm going to continue. So let's assume now that you have done what you need to do, which is page 1, and then when you get to page 2, so this here is taken from page 2. I'm going to put here page 2 from the worksheet. Eventually we'll get to this table, and then to complete this table I have to give you some information. So we're going to define the charge of an electron as well, in general, Q is the symbol for charge. So charge is in general represented by letter Q. Could be capital Q, could be lowercase q, doesn't really matter. Symbol or unit of charge is Coulomb, so it's just C, but let's see, did I spell that right? Maybe, but it's capital C for Coulomb, and then the charge of 1 electron, so I put here charge of 1 electron is the same as charge of one proton. Now one is negative, one is positive, but numerically they're equivalent, and that comes out to be 1.6 times 10 to the minus 19th coulombs. All right, so that value is important. You're gonna have to remember this one. Remembering this number is like remembering the speed of light. It's just something you should know. So charge of an electron is the same as the charge of a proton. The only difference is the quality of a charge. So charge of an electron is going to be negative. This is just by convention. Charge of a proton is going to be positive, and that's just by convention, but numerically they're the same, 1.6 times 10 to the minus 19 coulombs. So what I'm going to do with you is maybe one of the parts from problem 7. Number of exchanges and then quantity and kind. So maybe I'll do, I'm going to do part E. Right, so I'm going to do E from this problem. And so what we have to find here is we have to determine quantity and kind of charge. So let's do a quantity first. All right, so let me remove this out of the picture here. Let's just slide it somewhere out there, and I should be able to solve it in the space that now I have in front of me. So what I have is that there are, whatever the object is, the object now has 6.82 times 10 to the 12 excess electrons. All right, so excess electrons is what I have in the object. This is the number of electrons that I have, extra electrons in the object. So there's a lot of electrons, there's a lot of protons, but then I dump a bunch of electrons into this object. So maybe I can draw some kind of a surface. Right, and then on this surface, what I have is obviously there are atoms in it, and if there are atoms in it, then I have protons and electrons. So there's a lot of electrons, a lot of protons in it. But what happens is I dump a lot of negative charges here. So there's a charge here, and that charge comes from the excess number of electrons, and this is the number of electrons that I have. So to determine the quantity, what I'd have to do of the charge is I'd have to calculate Q, and Q would be, well, if one electron, so I'm going to put here, if one electron is 1.6 times 10 to the minus 19th coulombs, then it is pretty obvious that 6.82 times 10 to the 12 electrons, you'd have to multiply this number of electrons times the charge of a single one to get the total charge. All right, and so let's do this. So my calculator is giving me the following. I'm going to copy it like this: 2, 3, 4, 5, and then I have 1 coulomb. All right, so this is what I get. This would be the charge that is present here. So what I would write is that the Q charge of this object is now 0.000001 coulombs. All right, so that's part of it. What I just did is I calculated the quantity. So that somewhere here I would put, what was it, 0.000, how many do I have? 1 coulomb. That's the quantity of charge. Now, as far as the kind of charge is concerned, that would be whether it's plus or minus. If I have an excess of electrons, that implies that this thing must be negative. So negative is the kind. I'm going to put here negative. This is the kind or quality of charge. So it's minus 0.01 coulombs, right? And you'll do something similar for the other parts of this table. So now you can also do page 2 of this worksheet. So you should pause this video and then complete page 2 of this worksheet. So moving on to the next page of your worksheet, this title here is charge interactions. Can see it from what I've copied, but it says charge interactions. It's page 3 of your worksheet, so this is page 3. So well, let's state the obvious, and that is, let's say you take a positively charged object and you put it next to a positively charged object. What happens is you get repulsion, and this should be something that you are all aware of. You get negative and negative, and what you get is repulsion. and you get negative and positive, and you get attraction. All right, now this implies forces, and so what you get here is a repulsive force between the two, repulsive force between the two, and eventually we're going to start calculating these things, and here you end up with an attractive force. Now, but there's a bit of a twist to the story. So if you have, so on an atomic level, you either get protons, electrons, or you get neutrons. We don't go into any smaller parts. So for example, a proton is made out of quarks, 3 quarks, neutron is made out of 3 quarks as well. Electrons, as far as we know, are not made out of anything more substantial, more fundamental. But we won't consider any of that. On the atomic level, you're going to run only into protons, electrons, and neutrons. The story ends there. That is, if you have a proton and you have a neutron, you get no, this is neutron, you get no attraction, no repulsion. There's really nothing interesting. Well, I shouldn't say that, but there's nothing in terms of attraction or repulsion happening here as far as electrostatics is concerned. Likewise, if you get an electron and you get a neutron, there's no electrostatic attraction or repulsion happening. However, on a larger scale, this isn't so necessarily so obvious. So let's see how much more space do I have here. Okay, let's move this way. So let's say you have, now it's still true on a large scale that plus plus repels, minus minus repels, and then plus minus attracts. But suppose you have this. You take a charged balloon, and let's say you wrap this balloon with you know, a bunny fur. You take some rabbit fur and you rub it against the balloon, and then you end up transferring the electrons from the fur into the balloon, and so the balloon ends up with a bunch of negative charges here. All right, so this is the charge of a balloon. It's charged now. All right, now then you bring this thing close to a wall. So let's draw a wall. Here's a wall, and the wall is neutral. All right, so the wall is neutral, and then you have a balloon. The balloon is charged. Are you going to get any attraction, repulsion, or is there just going to be nothing happening there? Well, you're going to get attraction. In fact, the balloon is going to stick to the wall. And the question is, why is it that that's the case? So let's bring this balloon a bit closer. Well, actually, before I do that, let's draw, let's see what's happening here in terms of atoms. So within a wall, you're going to have these atoms. And let's draw these atoms. That's enough. Let me do another row, column. Here we have them. Let's, of course, what these atoms have are a bunch of positives. So let's put positives in the center, right? These positives would represent the nuclei. So we have nuclei. All of these atoms have positive nucleus. And then you have electrons, and the electrons are on the outside. So there you have electrons. Let's maybe draw like 4 per each. All right, so you have the electron cloud, where you have a bunch of electrons all over the place. I guess I should add more. All right, so we have, this is what we have. And then as you start bringing in, and these electrons are distributed more or less evenly, right? These electrons are distributed more or less evenly, so that you end up with neutral atoms, and the number of these electrons corresponds to the number of protons in each atom. All right, now, as you start bringing in this balloon, and so let's take the balloon and let's bring it closer to, let's bring it closer and closer and closer. Okay, it gets about this close. So what happens then is, as the balloon comes closer, it should be pretty clear that the electrons within the atom are going to move. Now, because this is an insulator, the wall is, oh, hang on a second, I gotta fix this. So but anyways, the wall is an insulator. So that means that the electrons cannot jump from one atom to another atom, but the electrons within the atom can still move. And so, you know, let's say these here will now shift a little to the right, so that you're going to have more electrons on that side and fewer on this side. Likewise, in the next atom, you're going to end up with shifted electrons. Like the actual electron cloud, the orbital is going to be shaped a little differently. Because of the presence of the electrons in a balloon, the orbital itself is going to have it's going to look a little more a little bit differently. Electrons will tend to spend more time on this side of these atoms. In the next column, the effect is going to be not as strong, but you're still, because of the distance, these are farther away from the balloon, but still the effect is going to be there, and so these electrons will tend to spend more time on the other side than on the first side. Now if you look at the wall here, well, first place, what we've done is we've polarized each atom, so each atom is polarized, right? Now you could redraw each atom and you could say, all right, here's each atom, and now what I have here is that the plus seems to be sitting a little farther to the left, and the minus seems to be sitting a little farther to the right. So each atom is now polarized. Like I have now a plus, let me just do one. I have a plus here, and then I have a minus on that side. But anyways, the wall towards the left now has a positive sign. And if the wall towards the left here has a positive sign and a balloon is negative, then the two must attract. So you're going to end up with attraction. Now, if the balloon instead was positively charged, the picture wouldn't really change. I could have redrawn this. I'm gonna do it only partially, but I'm not gonna go all the way. So let's say you removed electrons from the balloon, and now you ended up with a positive charge on the balloon, and then you have a wall. What happens in that case is that as the balloon comes closer, the electrons within these atoms tend to move towards the left. They tend to spend more time on the left hand side. Now you end up with a negative on you end up with a wall having a negative sign here. Negative and positive will attract, and so you're going to end up with attraction as well. So there's an attraction here. So in general, on a large scale, I'm going to put here, actually let me go back to this picture here. So yeah, so on and so forth, but on large scale, plus and neutral, not neutron, but neutral object. So positively charged object and neutral object, what we get here is we get attraction. Attraction, and a negatively charged object and a neutral object, what you get is attraction. All right, so to indicate this with arrows, you get an attractive force existing between the two. All right, between proton and a neutron, you do not get an electrostatic attraction. Between an electron and a neutron, you do not get an electrostatic attraction. But between positively charged object, larger positively charged object and a neutral object, you get attraction, and so on with negative and neutral. All right, with that, you can now go ahead and complete page 3 of your worksheet, and I think you can probably do page 3 and page 4. So do pages 3 and page 4 of the worksheet, and pause the video, do these 2 pages, and then come back. And there's one more somewhere here. There's one more thing that I'm gonna do with you, and there it is. All right, so what we have here is the Triboelectric Series. And so this would be like page. Let's see, this is page 5. So this is on page 5, and the top here, again, it's not showing, but what the top says is charging by friction. All right, that's page 5. Now, there's not that much here to say or explain except for this thing, Triboelectric Series. So the I see, I'm gonna move this way. It should be enough of room. If you rub together dissimilar materials, they have to be dissimilar. If you rub together dissimilar materials, then specifically if they're insulators. We'll get to conductors in a bit, so for the moment we're only considering insulators. If you wrap dissimilar insulators, electrons will be transferred. They'll just move from one place to another. Now the question is, which way will they go? And to determine that, you will use a Triboelectric Series. So for example, if you look at this Triboelectric Series here, we have a rabbit fur on the bottom, and then we have glass. So if you have a bunny, and you wrap bunny with glass, electrons will move from bunny into the glass. All right, let me take another case here. Let's say we have a cat fur here, and we have wood a little higher up, right? So it's cat fur, and there's wood that I see here. So I have cat. Let's say you wrap cat with wood, pick up some stick, and so if you have a cat, you have wood, the two come in contact. What happens is electrons will be transferred. Which way will they be transferred? They'll be transferred from cat to the wood. Why is that so? Because cat is lower on the series than the wood. So the electrons will always move towards the object that is higher up on the series. And with that, you can complete this worksheet, which is pages 5 and page 6, and that will do. Now, as far as the question, why is it that electrons are transferred up in this direction? The answer is we don't know. To the best of my knowledge, we don't know why electrons go from material A to material B, or at least that was the case about 5 years ago when I actually checked and I was trying to figure out why is it that electrons move from one substance to another versus in the opposite direction. And we can through experiments establish that they do move in a specific direction, but why is it exactly? Well, we can certainly speculate, and we have some reasonable guesses, but I don't think there's a consensus in terms of, yep, it's definitely because of, X that electrons move from cotton to wood. But anyways, Triboelectric Series, you can use that table to figure out which way electrons will move if the two substances that are dissimilar and they're insulators if they're wrapped together. So do pages 5 and 6, and that will do. Once you are finished with this, so pages 1 through 6, once you have finished them, you can check your answers. I think I will post the key on Canvas. I'm not entirely sure I will, but I think I will.